So the topic for today is persistent segment trees. And now I'll first define what a persistent data structure actually is. So starting from the term persistence, what does persistence actually mean? It means to retain. So a persistent data structure is actually a data structure that retains all the modifications that take place on that data structure. So starting with an example for a persistent data structure, I have a problem that I have taken from Anudeep's blog from persistent segment trees. It's a very good blog and it's worth a read for persistent segment trees. So the question comes as follows. We are given a linked list and there are two types of operations that need to be done on that linked list. The first operation being that we can update some initial X values on that linked list and the second is that we need to print the linked list after some kth update. So the point here actually is that the kth update, how do we print the kth update? In this case, we cannot update the X values as they come in because, for example, if we have some linked list like this and now I update the first two values to some new numbers which is let's suppose 5, 6. So my new linked list looks like this. And now if I update the first three numbers to some new numbers that are 7, 8, 9 respectively, then this is how my new linked list looks. So the point is that if someone now asks me to print the linked list after the first update, so actually I have to print this entire linked list. So this is how a persistent data structure works. It doesn't keep the updates in place. It actually does an update and then we can retrieve any update because it retains all the updates that are done on that data structure. So now, how to optimize the usage of a persistent data structure? That's the question for the day. Because if we construct a new linked list every time, then let's suppose we have n updates on that linked list of size n. So can you guess the complexity of this whole thing? Yeah. So the complexity would be O of n into n because each time we are constructing the entire linked list which is of size order n and we are doing this for n times. So this makes the complexity to be O of n square, which is not what we prefer. We can do something better. So I'd recommend that you pause the video and think of a solution to this problem. Yeah, so how to approach this? So the first step would be, let's assume we have 1, 2, 3 and 4. Now an update comes that says us that we need to update the first two values that are 1 and 2 to 5 and 6 respectively. So since we know that the other two elements of the linked list would remain the same, so for example, I get an update of so I'll do it like 5 and 6, and now since these are two elements, I'll attach it to the third element in the previous linked list, and this gives me a reduction because I do not need to create the entire linked list again. Now jumping on to the next thing, how if I get an element update, a 3-element update, which is 7, 8, 9, then what I need to do is that I'll write 7, 8, 9, and now where do I need to point the 9? The 9 would point to the 4th element of the previous linked list. So it will actually point over here. So I guess now I have made it clear how to apply this to the entire thing. Yeah. So this is how the updates will actually work. And now the entire thing would be that if we have an X element update, then we'll actually attach the new linked list of X elements. Let me clear the board. Yeah. So I'll attach the new linked list of X elements in front of the X plus 1th element of the previous linked list. Yeah. So basically, the X plus 1th element of the previous linked list would be the next element to the first X elements of the new linked list that's coming in. And this is how there would be a reduction in the space as well as the time. So now you have some time to guess what would be the complexity in terms of time and space for the new algorithm or for the new solution that we have. So it would be O of n plus x1 plus x2 and so on up till xm, where x1, x2 are the sizes of the element updates that are taking place, and this is the space complexity as well as the time complexity. Yeah. So this is a persistent data structure in the form of a linked list, and as we can see, we can actually keep all the updates that are taking place on the linked list as they are. So we can print the linked list after the first update, even after the second update, even after the third update, and maintaining the space and time complexity to be this. However, the main thing to note over here is, even if if all these X elements, X element updates are of order n, then our complexity would actually land up over here. But in the case where these element updates are actually close to order n, then our space and time complexity reduced to O of n, which would have stayed O of n square in that case. So now we'll be jumping on to the important topic of the day, which is persistent segment trees. Yeah. So coming on to the topic, persistent segment trees. So as we have got the clear idea of what persistence in data structure actually means, now we can easily understand what persistent segment trees would actually function like. So a persistent segment tree would actually keep all the updates that are taken place on that segment tree persistent, or we can say it that it will retain all the updates that are taking place. So let's assume that we have a segment tree, and as we all know that the segment tree has a divide and conquer strategy, so it looks something like this. Let's assume that we do a point update in some place on this segment tree. Like if I have a 4-element segment tree, then this would be one. These both would be two-sized nodes of the segment tree, and these all will be one-sized nodes of the segment tree. Yeah. So like if we have an update, let's assume these were 1, 2, 3, 4, and it was a max segment tree. So the value that would be stored over here is 2. The value here that would be stored over here is 4, and the value which would be stored over here is 4. So this is a max segment tree on this array 1, 2, 3, 4, which looks perfectly fine. Now if I want to update some element, let's assume that I need to make this one to be 5. So can you tell me how many nodes in the segment tree would actually change? So it's very clearly evident what are the maximum number of nodes that can change on a point update. So now the segment tree would look like 5, 5, 5, 2, this is the same, 4, 3, 4. So actually we can see that there is change only along the ancestors of this particular node on which the point update has actually taken place. That's the catch. So it gives us a login update. So basically we have login number of nodes that are actually updated. Because login is actually the size, or maybe I can say it order of login, and yeah, so login is actually the height of the segment tree. So yeah, this is the whole thing. So what better I can do to store all these updates? Like this is one update, so I don't need to store the entire segment tree as it is all over again. So what I can do is I can just keep some of the nodes to be the same and the others ones to be pointing towards the previous segment tree and removing this extra memory that is being required. So now we are just keeping 3 elements which are newly added. So this is how the segment trees function, the persistent segment trees function. They keep the pointers to the entire portion of the segment tree which was being used earlier, so that we do not create it repeatedly. And therefore, in persistent segment trees, we have O of log n time as well as the space complexity for each update. So we can now very easily print the segment tree after the first update, which is this. And for each update, we just need login information for that particular update. So this is the entire theory thing for persistent segment trees. Now we'll jump on to a question, and after that we'll see how we can actually implement persistent segment trees. The coding part would mostly be based something on pointers, because we need to use the portion of segment trees which were previously built for the new segment tree, so that each update isn't costly in terms of time and space complexity. If you have any doubts on this, you can go and read the Anudeep's blog on I don't remember actually. You can just Google search it, Anudeep's blog on persistent segment trees, and you can give it a read. I myself gave it a read when I was not able to get what persistent segment trees actually are. Yeah. So now let's come on to a question based on persistent segment trees. So the question is COT on Spotch. It's named count on a tree, I guess. So the question goes as follows. The question states that we have a tree consisting of n nodes. You can obviously read the question from the site as well. The link to the question will be below this video. And yeah, so the question is that we have a tree consisting of n nodes which are numbered from 1 to n. Each node actually has an integer weight. Here, not the edges. Instead, a node has a weight. So each node has a weight which can be any integer from minus 10 to power 9 to plus 10 to power 9, basically in the int range. So what you need to do is you need to print the kth integer or the kth integer weight from when you are traveling from one node to other node. So basically the query would be in this form: u, v and x, or basically k. So we need to print the kth element in the sorted order when running from node u to node v, or I can more clearly show it to you. So let's assume that this is our tree. This is node number 1, 2, 3, 4, 5, 6, 7. And let's assume this node has some weight 2, this has 1, this has 10, and this has 6. So, and some random weights to these as well. Let there be 6, 8, 9. Yeah. So, you need to, so for a query can be like 4, 3, 2. So, 4, 3, 2 means that on the path from the node 4 to node 3, we need to print the second element in the sorted order. So what that means is, first of all, we need to see all the elements that are present on the path from 4 to 3. The elements are 2, 1, 10 and 6. So we need to sort them first. The sorted order would be 1, 2, 6 and 10. And now the second element in this is 2. So the answer to this query would be 2. It's as simple as that. So this is the entire question. Obviously we don't need the brute force way. The brute force way is very simple. We just need to compute the LCA of the two nodes. Then we can run from this node to the LCA and from this node to the LCA again and put all the elements that come on our way. And once we are done, we just need to sort them and print the element that is on the kth position. But obviously this is not the required way because this is just a brute force approach to solve the question. So you can think of a solution using persistent segment trees as I described above before. So basically getting onto the solution is quite tough initially because you need to know how persistent segment trees can be used on trees. So actually this is a tree. Yeah. So I hope the question is clear. If it isn't, then you can see it on Spotch. It's named COT. So yeah, let's start. The solution would be something using persistent segment trees only, and this would how the solution will go. So first of all, what we need to do is we need to find the LCA. Yeah, so the first part would be finding the LCA for the two nodes U and V which I get. Let the LCA be L. Yeah, so this is a step which in which you can use a login approach, which would be shown to you in the LCA video, the lowest common ancestor video, wherein we can find the lowest common ancestor of two nodes in a tree in log n time complexity. Yeah. So the second step would be coordinate compression. Even if you are not getting things right now, you can just go through the video and you'll get it eventually. So the coordinate compression, as you may or may not know, it is something like reducing the values to a specific range. For example, let's assume I have some values ranging from minus 10 to the power 9 to 10 to the power 9. But there can be only at max 10 to the power 5 values, which is actually the case for our weights. The weights can range anywhere between these, but there can be only these many distinct values, let's assume, because there are only at max these nodes in the tree. So in this case, we can actually compress these values to some other values so that we can work on a segment tree. So the values like 1, 3 and 5, let's assume, can be mapped to 0, 1 and 2. And let's assume we have some 10 to the power 9 as well. So this can be mapped to So in this case, we can very easily see that the person who is bigger stays bigger here as well, which is the property which we need to maintain over here. So I guess this is clear. The next step is actually finding out the solution to the problem. So one thing that could come to anyone's mind would be something like a binary search. But binary search on what? Yeah, so a binary search can be something like this. So let's assume that I have all the elements from node 4 to node 3, or maybe from node U to node V. So I need to create some function f which gives me the number of elements that are less than or equal to x maybe. This can be described as the number of elements less than equal to x from node U to the root of the tree. Yeah, now things make sense. So the same function f for V would be the number of elements less than equal to x from node V to the root of the tree, minus f of LCA of U comma V x. This is actually the number of elements less than equal to x from the LCA of the two nodes to the root of the tree, minus So hopefully I'm making things clear over here. If this thing is not visible to you, then I can write it again. Then so this thing may be a problem for some people. I'll explain it to you. So actually, let's assume I had to find the number of like all the elements from 4 to 5 range in the path from 4 to 5, from the node 4 to node 5. Yeah, so I can include all the elements that are from 4 to the root of the tree, which is 1. So this I'll consider 2, 1 and 10, and then I can again consider all the elements from the node 5 to the root of the tree, which is 6, 1 and 10. Yeah, and now I need to subtract all the elements that are from the LCA of the nodes 4 and 5 to the root of the tree, which is 1, 10. And now if I write f of LCA UVX again over here, then actually I'll remove this 1 again, which is not the desired case. So I need to remove the 10. So what happens over here is this 10 gets cancelled from this 10, this 10 gets cancelled from this 10, and one of the ones gets cancelled because we cannot consider the LCA element twice. So this eventually leads us with 3 elements, which are 2, 1 and 6. So this is how this entire thing goes. So if we have some function f which can do this for us, then we just need to binary search. We need to binary search for all the x values, and since the x values have been compressed now, so I need to binary search for all the x values in the range 0 to n minus 1, where n is the number of distinct values. And this gives me the solution. But I need to binary search for this function, binary search on this function. So I need to figure out what this function could be that helps me in the binary search. So that function would come from the concept of persistent segmentaries, finally. I'll keep the question intact and this f function intact over here. So now let's assume that we have a segment tree. We have a segment tree at every node which can help us compute the f function. How simple that would make the things to be, right? So what that segment tree would actually store. So first of all, like in this case, we have the different values to be 1, 2, 6, 8, 9, 10. Since I'm considering the distinct values, I can remove this. And I can actually perform a coordinate compression over here. So 1 would map to 0, 2 would map to 1, 6 would map to 2, 8 to 3, 9 to 4, and 10 to 5. And now we'll go onto this tree. So if we are to maintain a segment tree at each node, so how that segment tree would look like is as follows. So since I have 6 distinct values ranging from 0 to 5, so and the first node contains a 1 over a 10 value which is mapped onto 5, so I'll mark a 1 over here. This is the array on which the segment tree up till this root node would be constructed. How would the array for node number 2 look like? You can pause the video and think of it. The value would, now it has a value 1 which is mapped onto 0, so it would look like something like this. The 1 here stays the same because it has to contain all the elements which are there in its ancestor and then add its contribution to it. So now I'll jump on to 2. How the array for the element number 2 would look like, on which the segment tree for that particular element will be built. This is node number 4 and the value is 2. 2 is mapped onto 1. So it will look something like this. Similarly, I can make it for 6. 6 has been mapped onto 2. So 0, 1, 2, 3, 4, 5. And now it looks like 1, 0, 1, 0, 0, 1. And similarly, you can construct it for others as well. So how would these segment trees help us is that if I can compute this f function on these segment trees very easily. So let's assume that x in my case is 4 right now. So f of ux is basically the sum of elements up till here. So this function, when binary searched, can give me the answer. So this function entirely should give me a value less than equal to k, or basically if I want the kth element, then this entire thing should be equal to k, I guess. Yes. So for the point where this value becomes equal to k, considering that x gives me the elements less than equal to x, then I can not be entirely sure, because it may happen that there is a 0 at the position of x. So instead, I should change this function to be number of elements less than x. But still there can be an issue, so keeping it to be equal only, because in any way if we are having a 0 over here, then that can cause an issue, because we cannot be sure whether this element is actually there or not. But the point I'm trying to make over here is that we can very easily find by doing it with a binary search perspective. Yeah, so the point where this whole sum, considering this to be a prefix sum, which obviously it would be, so where the first place where this prefix sum actually exceeds k is the point where my answer lies. So that is the point where I'll get the kth update. So I need to find first point where this is a prefix sum, because I'm considering all the elements which are less than equal to x. So it's giving me the count. So it's actually a prefix sum, considering I'm marking the frequencies over here for each of them. These are actually the frequencies. So if I get 6 below a 6, then then in the child of that parent, I'll update the value to be 2, means 1 for that 6 and 1 for that 6. So these are actually the frequencies. Yeah. So the first point where this sum becomes greater than equal to k is the point where I have the solution. But this can be done by a binary search. But the catch over here is that we are building a segment tree at each node. So eventually this will give us a segment tree of O n size over here, O n size over here, and this will eventually give us the complexity to be O of n square in terms of size. And the space would be a completely the time would be a completely different thing, because considering the time would be quite fine with this. Yeah, but the time would still stay out to be m into log n square, where m is the number of queries we have. One login in here comes from the binary search, and one login from in here comes from the segment tree part, the point where we are finding this function in the segment tree. But the point is, we need to first of all reduce this thing, and then we'll come over here. So I need to somehow reduce it to n log n and not n square. And this is where the strategy which I explained to you in the beginning will help us. Since I know the segment tree for this, there's only one update that the child of a parent brings into its segment tree. So that's where I just need a login nodes for that particular child in extra to the nodes of the parent. So the other nodes that aren't changed actually point to the nodes of the parent, and the nodes which are changed are actually created for the child again. So this is how there's a login extra space required for the child in comparison to the parent, and this would happen eventually throughout the tree. So each child would add login nodes. So eventually the space would be order n log n, which is our required space complexity. Hopefully I'm making things clear now. So yeah, this is how the structure would look like. And now we can see the implementation details when I write the code for it. The code would most likely be a different video, but till the time you are getting the objective of this, then it's fine. So this is how the things would be over here. So now we have reduced the space complexity. So it will actually function the same as the n segment trees would have functioned, but we have done this in O of n log n space by adding only the updated nodes and not the entire tree. Just the pointer way, which I explained earlier. Now the space has been reduced to O of n log n. Great. But do we actually need a binary search over here? So actually the time over here is log n into log n, which comes from the binary search part. I somehow want to reduce this binary search part in this. So how can we do things better? So now I'll jump onto the solution to this, wherein we'll be going on to a complexity which is like this, which includes the n log n for the construction of the segment tree and log n for answering each query. And since there are m queries, the complexity would look something like this. Yeah. So now let's see. Cool. N plus m log n is the space complexity. It's the time complexity for our solution. I'll write it again, is the time complexity. This is the desired complexity, and it is the complexity in which we can easily solve it. So actually these are actually 4 segment trees which we are referring over here. Am I making things clear for you? Because each node has a segment tree. Now we can always consider in this case that each node has its own segment tree, even though it just has log n nodes because of the thing I told you earlier. So these are actually 4 segment trees. 4 segment trees. These so the 4 segment trees are of the node U, the node V, the LCA of node U and V, and the parent of the LCA of U and V. Yeah. So these are the 4 nodes, the 4 segment trees which are into our consideration. So these would give rise to a new segment tree, which we can think in our perspective is a new segment tree, because actually they are updating values on the same array. So not exactly the same array, I will say, but yeah, they all have the same range on which they are working, which is from 0 to n minus 1. So I can consider that I have formed a new segment tree which actually works as follows, which is actually the sum of these two segment trees minus these two segment trees. So this is how our new segment tree would look like, and it would be constructed from the 4 segment trees that I have already explained to you. But the point is this consideration correct? Absolutely, because if I consider this, what this stores is all the nodes, it stores the frequency of everyone that's present from U to the root. This stores the frequency of everyone's that present from V to X, and so on and so forth. Same for this and same for this. So the new segment tree would actually just be a combination of all of these working on the same set of elements. So when the left of the new so the root of the new segment tree would actually be the sum of the values of the roots at these minus these values. And what would be the left child of the new segment tree? I need to go left over here, and subtract the left from here and subtract the left from here. So this is how actually things work. So the left of this segment tree is actually going left into this, and adding the values left of the left element of the left child of the root in this, and subtracting the values of the subsequent elements, subsequent nodes in these segment trees. So this may be a complex thing initially, but once you realize that these 4 segment trees will actually eventually lead to the formation of a new segment tree, which can be thought of as a virtual segment tree, then the things would be very easy for you. So now if I need to find the kth element, if I know that in the new segment tree I have 10 elements in total, wherein 6 elements lie over here and 4 elements lie over here. I need to find out the 8th element. So in my case, k is equal to 8. So I'm pretty sure that the k cannot lie over here. K will surely, the kth element would surely lie over here. So on this node, I'll subtract 6 from 8, and which will give me 2. So I need to find out the second element in this remaining part of the segment tree. And now let's suppose I have 3 elements over here and 1 element over here. Then I'm pretty sure that the kth element lies over here. And now if I have 1 element over here and 2 elements over here, then I know that 2 minus 1, the first element here which has a value 1, means which has a value greater than equal to 1, is the person that is the answer to my kth element query. And now if it has a 1-1 structure, then I know that it is this person. These are actually the frequency sums of all the elements that are present in that. So this means that there are 10 elements in total that are present, not necessarily distinct. Some elements can have values 2 of their frequencies, and some can have values 1, 3, 4, anything. So I now know that this is the person that I was searching for, and the position at which this number lies. Let's assume that this person lies at the position 8, sorry, 4. Let's assume. So in the coordinate compression which we did, I just need to store the reverse maps as well. So in this case, if 6, 8, yeah. So I know that if this is 4, then actually 9 is the number I was searching for. So this is how the entire structure looks like. And now I very easily know that I don't need to do this entire binary search thing over here, because this is actually a part of binary search. This is actually binary searching for the kth element, because in the log n size structure, but the log n here, instead of being multiplied, which was happening over there, is being added. So the complexity stays order of log n. The main thing over here, the gist is that you realize that these 4 segmentary summation would give me a new segmentary, and that would make things very clear for you. So this is the entire thing I wanted to explain. If I can make the idea for the new segmentary clearer to you, then I guess things would be more clear. So I just construct random 4 trees, one for node u. Segmentaries would actually be made on arrays. So like if I have something like this, then it may happen that something like this isn't possible, because I am assuming some things like I'm not taking into consideration that someone is the LC of other. I just need to make things clearer to you. So yeah, 1 0 0 0 0 1 and something like this, 0 1 2 3 4 5 0 1 2 3 4 5. Cool. And again I have so the new segmentary would actually, the point over here is that a segmentary is always, or in this case, is made on an array. So this will actually give me a new array. Yeah, so this is a very good thing to realize over here. So the segmentary is actually built on an array, and these 4 people will actually give me a new array. So like I'll consider this as 0 1 1 0 0. So actually I'll sum. The values over here would be summed and these would be subtracted. So array addition would be just adding the elements, subsequent elements that are present on a position. So if like I have 4 elements that are 4 arrays that are of equal sizes, then adding arrays is actually so the new array of I would actually be old 1 I plus old 2I. So if I were to add 2 arrays to form a new array, then I need to perform this for all I. For all I, new array of I is equal to old is equal to the position at old 1 and the value at old 1 at that position and the value at old 2 at that same position. So this is how things work. So here also I have a segmentary. Here I have an array. So subsequently I'll add zeros and again zeros, then 1, all zeros. Then 4 would be 0 0 uh, 0 0, yeah, and 5 would actually be 1 1 1 1, so it would be 0. 3 would actually be 0 actually, yeah. So this is how the array would look like. So the segment tree is built on this array, and therefore now you can very easily realize that these 4 segment trees would actually give rise to a new segment tree, and this new segment tree would be the basis for my construction. And now the sum of all of these elements is what is stored in the segment tree. So this is a frequency segment tree. Finally, I'll construct a frequency segment tree from this whole thing, and hence I'll be able to solve the question very easily. Now, jumping on to the next problem. Hope I have made the things very clear in this problem. Things would be clearer when we'll implement this. I'll jump on to some other question, and you just need to think of a solution to it. We'll implement all of these later on. So the next question is named mkth num on Spoj itself. So the question states that you are given an array again, and you are given queries like I, j, k, wherein you need to find the kth element from position I to j in a sorted order, just like it was given before. So let's assume like I have 2, 1, 3, 6, and I need to find out the 0, 1, 2, 3. So if my query is like I need to find out the third element from 1 to 4, then it will be 1, 2, 3, 6, and my answer would be 3. So it's almost similar to the previous question, but now I have got an array instead of the tree. How would you solve this question? Can you relate this question to the previous question? It's best in competitive programming to relate a question to some other question so that you are able to get or reach to a better solution for that particular question. And obviously if you have coded once for a particular question, then you know how to code it again, right? And this actually helps in competitive programming a lot. So you can take a pause and think of it. How I thought of this question was very simple, and after writing the code for that question, you just need to make one change and you have written the code for this question. So how is that possible? It's very easy. So if you can think of it, this is actually a tree again. The 0th node is connected to the first to the second to the third. These are all elements of the tree instead of an array, and this tree is a linear tree. The tree is linear, and now these are actually acting as integer weights to the nodes. Yeah. These act as integer weights, and so this question is again reduced to the COT question. And this is how I solved it. We'll be coding both of them. So any doubts which you are having right now would be cleared then. So that's all for this video. Thanks for watching.